Hello, my name is Matthew Llano, and I am a senior at the University of Oklahoma. Today I will be presenting over my experimental analysis of the bond between metal and carbon fiber composite with the Sooner Off-Road Engineering Competition Team. Sooner Off-Road is an engineering competition team that builds small off-road style prototypes for the Baja SAE competition series. This vehicle is shown in the lower right-hand corner. The team is currently interested in creating carbon fiber composite suspension links and drive axles. These are in hopes to improve the vehicle's overall performance of the competition by reducing the weight of the vehicle. The team currently runs steel drive axles and suspension links, shown in the upper right-hand corner. My research for the team will specifically highlight the bond between the carbon fiber composites and the metal fixtures necessary for the carbon to interface with the rest of the vehicle. The objectives are to first confirm the strength of the carbon fiber. After this, the carbon fiber will be bonded to 4130 steel using two types of epoxies at two different curing temperatures. The material properties of the adhesives used will then be determined in testing. To offer some background, currently carbon fiber composite suspension links are only commonplace in open wheel racing series such as Formula 1 or IndyCar racing. Drive shafts and drive axles, on the other hand, can be found in a number of OEM performance-oriented vehicles and even more when looking at aftermarket upgrades for standard road vehicles. As of right now, there are 4 Baja SAE teams that use carbon fiber composite for either suspension links or drive axles, and these teams consistently perform in the top 15 of the competition. One such example is Chico State Baja, shown in the upper left-hand corner, which partnered with QA1 to make custom drive axles for their 2019 competition vehicle. The issue with commercial off-the-shelf parts, similar to the one shown in the lower left-hand corner, is that they approach costs of nearly $2,000 and have the potential to limit the team's design goals. Having the ability to manufacture these carbon fiber composite components in-house would allow the team to design and manufacture to the exact specification necessary to achieve the best performance out of the car. As you may already know, carbon fiber composites have a very high strength-to-weight ratio, making it desirable for a vehicle such as ours. A perfect example of this is with a potential drive axle. By using carbon fiber composite, you can reduce the moment of inertia of the part with the same strength, improving the efficiency of the entire powertrain system. As I mentioned in the objectives slide, I will first confirm the strength of the carbon fiber samples. This is a necessary step to ensure that the failure modes when bonding the carbon and metal are consistently in the bond rather than the material themselves. The material properties will be determined using a standard tensile test and constructing a stress strain curve similar to the one shown on the right-hand side. Once the strength of the carbon is confirmed, single lap joints will be created to determine the shear strength of the adhesive. This will also be done using a tensile test by constructing shear stress and shear strain curves from the data. The single lap joints will look similar to the picture in the upper right-hand corner, and the tensile test data will look like the shear stress shear strain curves in the lower right-hand corner. For consistent results, a tensile testing machine was used. All of the tests were done on an Instron 5969 universal testing machine with a 5 kN load cell installed. This machine was available in Dr. Yingtao Lu's Micromaterials Laboratory at the University of Oklahoma. To ensure repeatability of all the tests, all samples will use the E8 ASTM specification for the samples. This was determined based on the theoretical strength of the carbon samples and the necessary width that would allow for failure with the 5 kN load cell. As mentioned previously, the carbon fiber samples were tested to confirm their strength was equal to or greater than that of 4130 steel. In this sample, shown on the left, we see that the failure was within the sample area, which is necessary for consistent data. From the graph, we can see that the yield strength was 72,500 psi, with an ultimate tensile strength of 73,800 psi. In the second sample tested, the yield strength was determined to be 64,000 psi, and 64,700 psi for the ultimate tensile strength. Changes in the values were determined to be due to a small slip in the jaws that might have altered the data. There were 5 samples tested, and of those, these 2 were the best, which had the smallest amount of slip. And regardless of that small slip, the carbon fiber samples were greater strain strength than the 4130 steel that they would be bonded to later in the research. I created the first single lap bonds with West Systems 105-206 resonant hardener, which is an impregnating epoxy. This was chosen because it's what the team believes was used in previous research done on carbon composite suspension links. There were two samples made, one cured at room temperature and another cured at 170 degrees to increase the viscosity of the epoxy and reduce the number of air bubbles in the bond. All the bond areas were chosen to be half an inch squared, and the bond surfaces themselves were treated in the same manner by sanding with 300 grit sandpaper and cleaning with 90 proof alcohol to ensure the bond surfaces were clean. The results of this test are what one would expect for an impregnating epoxy, which had a very low shear strength of only 81 psi. What's shown on the slide here is only the 170 degree cured sample, as it was the better of the two. From what we can see in the graph, the final result was actually extremely flexible and gummy, and the machine didn't even recognize that the bond had failed and therefore ran until there was zero stress measured. Based on the results, I created more samples using LORD 310A to B adhesive epoxy. This epoxy was chosen because it is available on McMaster car, and it was very important for the team that the adhesive chosen would be easily available and relatively affordable. The samples were cured at both room temperature and 170 degrees Fahrenheit. A big difference between the adhesive epoxy and the impregnating epoxy is that increasing the curing temperature does not improve the viscosity of the sample, but instead reduces the curing time, which would be important for the team when needing to make quick adjustments at a competition. Similar to the test done with the West Systems epoxy, all samples here were treated with 300 grit sandpaper and cleaned with 90 proof alcohol to ensure the bond surfaces were as clean as possible. The tests were done using a much smaller bond area of approximately a 1/4 inch squared, after tests conducted with a 1/2 inch squared bond area had inconsistent failure modes. The sample shown here was cured at room temperature. The results of this test are shown on the right, with a small anomaly where the yield stress caused a large dip in stress, which is not typical for adhesives. Because of the anomaly in the previous test, another one was conducted, with another sample cured at room temperature. This sample had an ultimate strength of 1600 psi, much higher than the previous sample. Finally, a test was conducted with the adhesive cured at 170 degrees Fahrenheit. Because adhesive epoxies cured at higher temperatures have a reduced curing time, which would be desirable for the team in the event of a repair being done at a competition. This resulted in a slightly lower shear strength of only 1200 psi. There was a slight anomaly in the results given from the Instron machine, where it measured more stress after the ultimate tensile stress, rather than dipping off as necessary. This was overlooked because the overall strength of the sample was already determined. Based on the test done, the ultimate strength of the LORD 310A to B epoxy was determined to be 1,600 psi when cured at room temperature. This was deemed suitable for the team based on the forces that the suspension links and drive axles exhibit throughout driving at competition, which means that the contact area for these will not need to be an exorbitant length that would mitigate the benefits of using a higher strength-to-weight ratio component such as carbon. The ultimate strength of the LORD 310 was cured at 170 degrees was 1,200 psi, which was still suitable for the team to make quick repairs at competition. The reason this is still suitable is that the team designs with a safety factor of above 2, and so having a reduced strength would still meet the application when driving in typical scenarios, but obviously if an extraneous situation was encountered again, it would fail much sooner than the 1,600 psi strength. My final conclusion for the team is that they should use the LORD 310 epoxy, mostly because it is readily available on McMaster car at a relatively low cost when compared to other adhesive epoxies. Based on this though, I will still warn the team that there are a number of manufacturing inconsistencies that can lead to varying strengths of the bonds, and therefore all parts should be tested statically prior to driving to ensure the safety of all drivers, and that a component critical to the maneuverability and handling of the car and safety of the drivers does not fail prior to them driving. I would like to thank you for your time, and I hope that what was presented today was informative on other carbon bonding applications.